Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, find number of ways to reach the kth stair. The problem is like any other dynamic programming problem with recursion, but if you face difficulty while solving this during the contest, then this video is for you. And I'm very sure if you stick till the end, you will be able to learn at least few new things and able to approach these kind of problems by yourself in future contests. So with that, let's get started. The problem states that you are given a non-negative integer k and there exists a staircase with an infinite number of stairs with lowest stair numbered 0. Now Alice has an integer jump with initial value of 0 and she can start on stair 1 and wants to reach stair k. There are two operations which Alice can do. One is she can go down from ith stair to I minus 1th stair, and this operation cannot be done consecutively 2 times, or it can be done when Alice is already on stair 0, which is the smallest or lowest stair that we have. And the second operation is Alice can go up to stair I plus 2 power jump and also increment the value of jump to jump plus 1. Right, so she can do these two operations as many times as she wants, and the problem is to return the total number of ways Alice can reach the stair k. Right, now let's take an example. Let's say k is 1, so Alice is starting at stair 1 and we want to know how many different possibilities are there in which Alice can reach stair 1. So first way is Alice will not do anything because she is already standing on stair 1. So that's one possible case. Second is Alice will do operations of first type, that is jump to stair I minus 1, and after that she take operation of second type, which is jump to stair I plus 2 power jump. Notice jump was initially 0, so 2 power jump is 1. So the first operation is go from 1 to I minus 1, which is 0, and then from 0 to I plus 1, which is 1. So 1 to 0 and 0 to 1. So Alice is at stair 1 again. So that's the second possibility. Then similarly, the third one would be, instead of applying this operation first, Alice will apply second operation first. So notice jump is 0. So after applying second operation, Alice will go from stair 1 to stair 2, and after that she can apply operation 1, and from stair 2 she can go back to stair 1. So again, that's the third possibility. Now the final one is she will start with the operation of first type, go to stair 0, then she will take operation of second type and reach stair 1, and then again take operation of first type to go to stair 0, then again take operation of second type to go to stair 2 this time, because whenever you do operation 2 you have to increment the jump. So initially jump was 0, so you made a jump of 2 power 0, but then the next time you have to apply that operation, you have to make it 1 greater. So this time you made a jump of 2 power 1. So from 0 Alice will go to 2, and finally from 2 again apply the operation 1 to come to 1. These are the four possibilities in which Alice can reach stair 1, and hence 4 is the answer. Right, so hope the problem statement is clear. Now how to solve this? We have these two operations, that is first Alice can jump from I to I minus 1, and notice it can't be used consecutively, and second is Alice can jump from I to I plus 2 power jump, and also we have to increment the jump that we have currently. Right, so these are the two operations we have. Now let's try to simulate a few operations by hand and see if we can observe something. Right, so Alice is starting at index 1. Right, now what would happen at index 1? There are two choices only. Either you will apply the operation of type 1 or you will apply operation of type 2. So at index 1 there is no constraint, because you haven't applied any operation of type 1, so this cannot be consecutively, constraint is not there. So either you can go to 0 or you can go to 2. Now notice when you go to 2, the value of jump that you have will be 1 now, because it will also be incremented when you do the operation of second type. So these are the two possible choices. Let's assume for now that you went to 2. Okay, so that's the assumption. Let's say now you are at 2. Now your final goal is to reach k, and let's say k is 8, for example, right? So we want to reach 8 and we want to find out how many different ways are there to reach 8. Now from 2, what we want? We again want to reach 8, and we want how many different ways are there to reach 8, right? The only difference now is the first jump that you can do at 2 can either be at 1 or it can be at 4, right? Why? Because j is now 1, and because j is 1, the jump that you will take using operation 2 will be of 2 power 1, which is 2. So from 2 you can go to 1, that's fine, but from 2 you can't go to 3, rather you have to go to 4, right? So that's the difference. Now from 1 you wanted how many different ways are there to reach 8. Now from 2 you wanted the same thing, how many different ways are there to reach 8, but just one different constraint, that is the value of j, or value of starting point where you can jump from, has changed. Hope you can see similarity between the two problems. If not, let's do one more iteration. Let's assume that when you were starting at 1, instead of taking the route of 2, you have taken the route of 0. Now if you have taken that from 0, what you can do? You can't go back. Why? Because there is nothing before 0. So only thing you can do is go forward, and you can now go forward one step, because j in this case is still 0, because you haven't applied operation of type 1 here, so j is still 0. So the first jump you will do is of jump 2 power j, which is 1. So again from 1 you went to 0, and from 0 you want to go to 8 only. So you again want what is the different ways to reach 8 from 0 given j is 0. So hope you can see the recursion here. Let's try to formulate it a bit more. So what we are saying is, from starting point I, let's call this I, we can do two operations. Either we can go back to I minus 1, or we can go forward to some I plus 2 power j, right, where j is the starting point or the starting jump you can do using operation 2. So basically your state is I comma j, that is you're saying if I am standing at index I and the starting jump that I can do is of j, give me the minimum, give me the different ways to reach k, right? And when you make any of these jump, these two variables will change, and you again want the exact same thing. That is, let's say you reach 2, so you'll say, okay, starting at 2, give me the number of ways to reach 8 or k with this j as the starting point. So hope that recursion state is clear. Let's try to write it down a bit formally. Our function f denotes what is the minimum number of what is the total number of different ways to reach k starting at I, and this jump denotes what is the jump you can make using operation 2, because all of the previous jumps you might have already made, right? Now there is third state as well, but let's talk about it a bit later. So let's assume this f of ij is there. Now from f of ij, what you can do, you can either go back using operation 1 or go forward using operation 2. So if you go back using operation 1, you will be at I minus 1, Jump will not change because you haven't applied any operation 2, so jump will stay what it was, and we'll talk about false later on. And other ways, you go to I plus 2 power j, and then jump will change to jump plus 1, right? The j is equals to jump, this is just for cleanliness. Now once you figure out these two values, what this denotes, it denotes starting from I minus 1. If my starting jump for operation 2 is jump, tell me what is the total number of ways I can reach to k. Similarly, this denotes starting from I plus 2 power j, where initial jump is jump plus 2 power jump plus 1. Give me the total number of ways to reach k. Now let's say this gives you x and this gives you y. So total number of different ways to reach k would be x plus y. Why? Because you are saying that there are x different paths from here. You are saying there are y different paths from here. So from here, how many paths will be there? X different paths, right? Plus y different paths, right? So total number of different paths would be x plus y. Now there is one small thing which is remaining. We haven't taken care of, cannot be used consecutively, right? Because if we have applied operation 1 just now, we can't apply that operation again. So when you are saying that starting from I minus 1, give me the total number of ways to reach k, you have to, like, you can take either operation 2 or operation 1, right? Now this path might not be feasible at all if you have reached this I minus 1 via operation 1. So if you have applied operation 1 here, in the second path you can't apply operation 1 again, so that is not possible. So to ensure that this information is with you, you can forward that information for along when you are calculating the next value. That is, when you are saying that I want total number of ways starting at I minus 1, you can say that, okay, notice I have just applied operation 1, so make sure whatever constraint you need to validate or you need to abide by, you should abide by that, given I have just applied operation 1. So in this case, instead of saying that is the previous operation is operation 1, we are saying can go down. Like, you can, instead of this, you can say what is the previous operation, and that would also suffice, and based on that you can define what can be the next operations, right? So basically we are saying what we have done previously and what we can do now. So hope this recursion is clear. If not, we will be doing a full dry run of this sometime later, so that will be clear at that time for sure. For now, what you understand is starting like this particular state, why we have three things here and what these three things are doing, and if like, is it possible to remove any of these, is what you have to understand. Currently it's not possible to remove any of these. They all exist because of reason, and that reason should be clear at this point, right? Now if this is clear, there are two things in any recursive solution which we need to take care of, and whenever we discuss about these dynamic programming problems, these two things are kind of self-evident, but in this problem it's not the case. So what are those two things? The two questions are, is there a loop? If there is a loop, you can't use recursion, right? Or you need to come up a way to remove the loop while using recursion, right? So this is an important question. Usually we don't ask this because the state itself is so clear that we can understand that, okay, there should not be any loop, right? Second question is, what is the base case, right? Again, this is also something which is clear in most of the scenarios, but in this case it's not very clear, because one might think that if I reach index k, that is my base case, but that's not currently fully correct, because we just have seen that for k equals to 1, we have reached k before multiple times and still we were continuing our operations. So base case can't be simply like if I equals to k, then just return 1 or return 0. That can't be the base case. You have to define that base case more intelligently. So these are the two questions we need to answer. Now if you understand any of these two, like we will be discussing these two questions in the next 5 to 10 minutes of the video. So if you understand any of these, feel free to jump to the next section. All the timestamps should be there in the description down below. Now first of all, why cycle matters. If you are still not convinced that if there is a loop, like why should a loop matters in recursion. So let's try to understand that first. Let's say the problem statement is starting at 1, give me what is the minimum distance to node 3, right? Now this is a graph. You can use Dijkstra or any other storage path algorithm, that is completely fine. But the thing is, you can also think of it, or rather you should understand why Dijkstra, why we are applying Dijkstra and why not dynamic programming. Because if you think about it, it is very similar to the previous problem we are solving. We are starting at here. Now from here we can go to 2 and we can ask that, okay, what is the minimum number of nodes or minimum distance from 2 to 3, and whatever is that, we will add 2 to that, and that will be the minimum distance from 1, right? So it's very similar. You can say that, okay, if I am at I can go to all the children of I, ask their minimum distance, take the minimum across all of them, and that will be my answer, right? So that is very well a solution. But in this case it will not work. Why? Because let's say you are calculating f of 1, right? Now from f of 1 you want minimum, again f of 1 denotes what is the minimum distance from 1 to 3 or to k, where k is 3 right now. Now from f of 1 you go to f of 2 and say, okay, what is the minimum distance from 2 to 3. Now from f of 3 you can go to f of 3, right? Now from f of 3 you can directly return 0 here, right? But let's assume that there is a like there can be different paths to 3, right? So let's say from 3 you want, or let's say k is 5, right? You don't know 5 exists in this entire cycle or not, but let's say you want k equals to 5 and you want f of 5. From f of 3 you wanted f of 4, right? Because you are saying that, okay, starting at index 3, give me the minimum distance to 5. So from 3 you can go to 5, so you'll say, okay, starting at 4, give me the minimum distance to 5. Now for f of 4 you want f of 1, right? You will say, okay, starting at index 1, give me the minimum distance to 5, and given I am starting at, like, whatever is the minimum distance to 5, I will simply add back here, and that will be the minimum distance to 5 starting at 4, right? But now you can see, to calculate f of 4 you want f of 1, but to calculate f of 1 itself you indirectly want f of 4 as well. So basically you can't calculate any of these without calculating like without breaking this particular cycle, right? So that's where cycle matters. Now let's do this one more time on an acyclic graph. This is a cyclic graph, but this is the same graph with acyclic. We just reverse this edge and this graph become, there is no cycles in this graph. Now if you do the same thing here, it will not be the same case. For example, from f of 1 you will say, what is the minimum distance to 5? So you will say, okay, I want f of 1, so I will say, let me figure out f of 2, and whatever is f of 2 I will simply add 2, and that will be my answer for f of 1. Now from f of 1 you are saying that, okay, I want f of 3 first. From f of 3 you are saying that I want f of 4. Now from f of 4 you are saying that, okay, there is no path at all. So basically there is no 5 at all in this graph, so I will simply return, let's say, infinity from here, right? So notice you are starting calculating the value. So f of 4 is infinity, f of 3 will also be infinity plus 5, which again is infinity. F of 2 will be f of 3 plus this edge, which is 4 plus infinity, which is again infinity. So we will say f of 2 is infinity. Now f of 1 would be infinity plus 2, which is infinity. So f of 1 will also be infinity, right? From this path. Now there is another path which is you can go to f of 4 as well. You can say, okay, I have two paths, from 1 I can go to 2 or I can go to 4. So let me figure out what is the total distance, what is the minimum distance from 2 to 5, what is the minimum distance from 4 to 5. Whatever is minimum, I will take that and calculate the minimum distance from mine. So f of 4 we already calculated infinity, so it will be infinity, and everything will be like this. From this path as well you will getting infinity, so the total distance from f of 1 to 5 would be infinity, right? So hope you now are convinced that cycle does matters, and in usual recursion or dynamic programming problems we don't care much because that is self-evident. So now, if cycle matters, first question we need to ask us is cycle possible here? And if cycle is possible, we have to think of something else, or at least try to think of a way to break the cycle, right? So in this case, cycle is not possible. Why? There is a few examples in this slide. You can pause the video and try to think by yourself. So you are starting at, let's say, f of I jump true. Now if there is a cycle, that means from f of I jump true, after following some path, you reach to something, and then from there you again reach to f of I jump true. If this is possible, then there is a cycle, right? Now if we need to prove that there is no cycle, we need to prove that there is no such path like this exist ever, right? So in this case, what are the two choices? From f of I jump true, you will either go to f of I minus 1 jump false, or f of something which is I plus 2 power jump. So that's not relevant here. So something to jump plus 1, and it will be true only, but that also doesn't matter. So in this case, you are jumping to jump plus 1 with some I, right? Now once you have jumped to jump plus 1, there is no way you can go back to jump, right? So if this node has the value of jump as jump plus 1, then there is no such path exist, right? And if we follow operation 2, we will be going to j plus 1, and hence this path doesn't exist, right? Now the only thing we need to prove now is the cycle or this kind of path possible via operation 1. So from operation 1 we go to f of I minus 1 jump false. Now from here we have just one choice, that is something to jump plus 1 to false. So from here let's say this is one such path from I jump. Now from here there's just one choice. The choice is you can go to jump to a node with the value of jump plus 1, right? And if you are going to a node with jump plus 1, you can't reach to jump again, right? So cycle is not possible via this path as well, right? Now there's one more case. The case is we have started with something which is true. What if we start at false? The case is very similar. I would again encourage you to pause and try to think. So again we need to prove that there is no such path that if this goes to a node and from that node you will come back to this. We need to just prove this. Now again we'll do the exact same thing. Let's say from I dash, from this state, the only possible thing that you can do is to go to jump plus 1. And if you are going to jump plus 1, again sorry, this will be true I guess, right? So again that doesn't matter much. So if you're going to jump plus 1, it means the only way this will be colliding with anything else if this is already computed, but we are currently at jump, so jump plus 1 is something which is not computed for sure. So one more way to think about this would be, let's say you are filling up this matrix as a part of your dynamic programming. So let's say this is jump and this is jump plus 1, right? Now if you are here and you are saying that from here I can go to here and from here I can go to here, like here, or so on and so forth. So basically if you can go only forward, then there's no possibilities of cycle. But when you are saying that okay, from here I will go to here, from here I can go to here, and now from here, let's say I can go to here. Now the only way possible would be like from here as well you come to here, but notice this is not a cycle, this is acyclic, right? So even though this part is possible via this route, we will never be having a cycle if we go to jump plus 1, right? And that's basically it. You have proved that there is no cycle in this tree which will be expanding whatsoever. Now the only other question you need to ask is what is the base case? So I would strongly encourage you to pause and try to think about the base case by yourself. So next we will be doing a dry run, and after doing the dry run we will be understanding what would be the base case, or rather through dry run we will understand why base case matters here, right? If that part is still not clear. So let's assume that k is 3, that is starting at stair 1. Why 1? Because it's given that Alice is starting at stair 1, right? So starting at stair 1, we want to go to stair 3, and we want to know what is the total number of ways to do that, right? So remember the state was I jump can go down. So I is 1 because we are starting at stair 1. Now jump initially would be 0, right? Can go down is true because from 1 you can indeed go down because you haven't taken any of the previous operations, and stair is also not 0, right? So from here, what are the choices? So either you can take operation 1 or you can take operation 2. If you take operation 1, you will be going down one step, and operation 1 is possible because can go down is true, right? So if you do this, you will be going from 1 to 0, and jump will not change because you haven't applied operation 2, right? Jump will only change for operation 2. Just to recap, jump will only change if you have applied operation 2, otherwise jump will stay as it is, right? So from f of 1 of 0, you are saying that you will go to f of 0 comma 0. Now this true will become false because you have applied operation 1 here, right? And once you have applied operation 1, you can't apply operation 1 again. So basically we have said that now you can't apply operation 1 again, right? You have to first apply operation 2, and then you are eligible to apply operation 1 again. So from 1 comma 0 comma true, you can go to 0 comma 0 comma false. Another way would be you can apply operation 2. If you apply operation 2, the jump you will be having is 2 power 0, which is 1. So from 1 you can go to 2, and notice you have to, because you have applied operation 2, you have to increase jump as well. So jump would be 0 plus 1, which is 1. Now because we have applied operation 2, you can still apply operation 1 afterwards, right? So this is still true, right? Similarly from 0 comma 0, you can go to 1 comma 1 comma true, because the only thing possible here is operation 2, right? And if you apply operation 2, you will be jumping ahead 2 power 0 steps, which is 1 step. So you will be jumping 1 step and reaching to 1, and your jump will also increase because you have just applied operation 2, and this false will become true because you have applied operation 2. Now you are eligible to apply operation 1 as well afterwards, right? In the same fashion, if you keep on expanding this, you will be getting some 3 here, and because you got 3, it doesn't signify that you can't get 3 afterwards, because you have gotten 1 here, you got 1 again here, you got 1 again here, right? So there are multiple, you got 1 again here, so there are multiple different places where you can get 1, right? Even if you get 1 before. So it may be possible that if you got 3 here, you may got 3 again. So let's continue moving forward. So that's where this recursion needs to stop somewhere, right? If you continue moving forward, this will go forever, right? Because you are incrementing things, you are not decrementing, so it will go on forever. So you need to stop at some point. Now what is the correct stopping position of your recursion? That's the last question or the last puzzle in this problem. So what you are doing, you are saying that from a stair or from a node, I can go back 1 step or I can go forward 2 power j step, right? Now, if you are going 2 power j steps forward, you are saying that you can go back one step, and from there you again have to go 2 power j plus 1 forward. There is no other choice, right? That's what the problem is saying. So because of this constraint, do you ever think that if you have if the value of 2 power j is greater than k, then even though you take a backward move, your forward move will cross k altogether and you will not be able to come back to k, right? Just to reiterate, what we are saying is we have to find out a point where we can stop. Now we have seen that if we already got k, it is possible that we still get k afterwards, so we should not stop here, we should continue. Now how long to continue is the question we are trying to answer, and for that we are saying that if the forward jump value is greater than k, or let's say for safety 2 into k, again why 2 into k, will come to that, but if the forward jump is greater than some multiple of k, then whatever you do after a move, you can only go to that node minus 1, and after that you have to again go and jump more than k. So in this fashion you will never be able to reach k back again. So once you have passed this point, you can stop. Basically, if the value of jump or the value in this second place of this recursion is greater or 2 power that value is greater than some multiple of k, or for simplicity, like either this is true, but if you are uncertain you can do 2 into k as well, that's fine. This will not be true only in I think 1 or 2 scenarios which you can enumerate, that is when the value of k is very small, but for others this would be correct, but for safety you can still take 2 into k. And if this is happening, then you don't need to go forward, because going forward will only increment j, and the gap will keep on increasing and you will never be able to come back to k, right? So this will be your base case, right? So we have discussed all the things. I am not showing you the pseudo code because I want you to code this entire thing yourself. This is very simple recursive state that we have figured out with some base cases, right? Now what is the time complexity? The time complexity would simply be number of different states multiplied by what you are doing inside each of the state. So inside each of the state we are simply doing 2 more calculations. We are calculating f of 0 comma 0 comma false plus f of 2 comma 1 comma false, and to reach at these 2 states, what we are doing is, in worst case we are calculating 2 power j, and calculating 2 power j is straightforward for if j is less than equals to 60. Like you can simply use bitwise operator and do it in order 1. Even if you don't know how to do it in order 1, you can simply run the loop for j times and you can do it. Now what is the maximum value of j that you can have? The maximum value of j would be, just take log of both sides. This j will come here if you take log, and this will become log k. So maximum value of j would be around log k, and k is 10 power 9, so maximum value of j would be log of 10 power 9, which is like around 30, right? So inside each of the function you are doing at max order 30 operation. Again, you can do it in order 1, but just in case you don't know, you can do it. You are doing in order 30 by simply running a for loop and calculating 2 power j. Now how many states you have? Again, notice you have to do memorization for sure, because without memorization it will not pass. You can see f of 3 comma true occurs multiple times, and if you have expanded this entire thing already, you should not expand this again to avoid exponential time complexity. So because of that reason you have to memorize this entire thing. Now because you have memorized, you will be computing one state exactly once, and to calculate one state you have figured out that it requires constant time, so let's not worry about this. So it requires constant time to calculate one state. or let's make it log k itself. So it requires log k time to calculate one state. Now how many states are there? Number of states would be number of different values of these three variables. Jump would be log k. We have calculated that just a while ago. Can go down, there are two possible values, true and false, right? Now number of different values of I, that I leave you to exercise. I would be directly dependent on log k itself. Just think about it, and this will be of the same order, and the entire complexity would not be greater than log cube k, and that is sufficient to pass the given time constraint, right? So hope the entire problem is clear. If you have watched this point, would strongly encourage you to pause and try to code, because the time you are coding, that's the time you will understand what you don't understand. So let's look at the code. The code is exactly what we just discussed. We have this function f, just call it f for now. This function f takes in three things: which stair you are at, what is the starting jump, and whether you can go down or not. Now this is a base case where we are saying that if 2 power j is greater than 2 into k, we will simply return 1 or 0 based on which state we are at. So if stair is k, we return 1. If stair is not k but stair is k plus 1 and we can go down, then basically we can go one step down, so that is returning 1. I think we can remove this, but I put that for safety. Then this is the usual recursive memorization thing. Now why this is a bit complex here, because the value of stair is, even though the distinct value of stairs is less, the value of stair itself can be huge, right? Because the value of stair could be of the order of 10 power 9 only, but number of distinct values of stair which you will be interested in will be smaller, right? Just think about it, and we can discuss in comment section if you are still not clear. So this value can go very high, but number of distinct values is small, so we can enumerate it in a table. That is something we are sure of, but we can't have all possible states in the table. So that's where we simply kept a unordered map to avoid having an array and hence filling up all the states to 10 power 9, because all of them will not be needing, right? Now what we are doing is simply we are going, these two things are smaller, so we make them as an array, regular array, and then this is an unordered map, so we are simply figuring out the value at stair, right? So after that we will be doing two things. If we can go down, we will go down. If not, we will go forward for sure. If you go forward, the can go down will be true. If you go down, the can go down will be false. That's it. And finally we'll save this as well to avoid recomputation. So hope this entire thing is clear. Any doubts, feel free to post them in the comment section below. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.